B with the extra credit, and then there's a final project. Okay, that's what's coming. All right, so last time we were talking about the general theory of open quantum systems. As we've discussed, we've been dealing with, when last semester in quantum optics, we had the optical block equations, and we included phenomenological T1 and T2 time, which involved dephasing and population decay, but they were put in phenomenologically in the same way that in classical mechanics we put in a friction coefficient without kind of deriving it from any first principles. We just see this as a phenomenon, and it describes, it's a good description, but it's how it arises from basic principles. It's not something we typically worry about. And in a similar way, we can do that in quantum mechanics, and we can put in damping. We have to be careful in certain ways to, not violate loss of probability and things like that. But if we, kind of do it phenomenologically, we can get away with it. But it's nice to understand where this comes from first principles, and also gives us a deeper understanding of the nature of open quantum systems and its relationship to measurement, and also ways in which we might want to derive it in certain circumstances. We want to understand the model in more detail. Okay, so that's our motivation.
What's R and S and C?
I'll explain this. You got it, and then when I get to it, I'll get to it.
Thanks.
So let's go through this, and then
Right. Yeah. Okay,
so
sorry.
so some of the phenomenology that's important here, when we have an open system, is that we have dissipation, we have dynamics that are no longer time reversible. We can see a change in entropy in the system that's related to the fact that information can be lost from the system into the environment. All of those things are things we see in classical dynamics as well. A kind of uniquely quantum aspect of this is the notion of decoherence, and that will be an important topic of discussion. Right. So a kind of fundamental way of getting at the kind of dynamics that arise when we have an open quantum system is to think about what we call a quantum channel, which is a kind of general input-output map for quantum states. Okay, and so what do we want this map, if we don't even know where this comes from, what do we want this map to do? We'd like it to take a physical state to a physical state, right? And a quantum state is defined by a density operator, and a density operator is a Hermitian operator with positive eigenvalues or non-negative ones, right? And so we want this to, such a map that does this is called a positive map. Now, technically, the maps we're really interested in are what are called completely positive. It's a very technical thing, but what it basically means is the following. Suppose we have a map that acts on some quantum system, but there might be some reference system, I'm calling R, that's around that the environmental degrees of freedom are not coupled to, okay? And so the system I'm looking at might be a subsystem of a bigger thing. There might be some other reference system around. But we want this to take this state on S to a positive state, regardless of what the reference state is. If it does that, it's called completely positive. There are mathematical operations which are positive that are not completely positive. For instance, the partial transpose is an example of that. And there's no way to think about the partial transpose as a kind of mathematical thing, but it's not a map that we think about as a physical map, okay? So there are maps that are positive, they take positive operators to positive operators, but they're not completely positive, and those are the ones we care about because of we want them to, it shouldn't matter that there's some reference system around. Okay? Okay, now it turns out, in ways that I'm not going to derive here, that having a map that's completely positive is equivalent to what's called a measurement model. Now, I'll explain why this is called the measurement model in just a little bit. But the measurement model is to say this map I think about as, okay, I started out my system uncorrelated with the environment. And I'm going to take the environment to be in some fiducial pure state. As we said, it's really not important that this is a pure state. I could do this for an arbitrary state. But what's important is that initially they're uncorrelated. And then they interact. And they interact because there's nothing else around by unitary evolution, which will generally be an entangling unitary that correlates the system and the environment. And what we find in that case is that that's equivalent, I can actually switch this, these are all equivalent, that this map is what's called a Krauss map. Okay? So any completely positive map is a Krauss map. As we also describe, the Krauss operators here, which I also like to call the measurement operators, because of the relationship here to a measurement model, are not unique. I can do what's called a unitary remixing of the Krauss operators. Really, this doesn't even have to be a unitary matrix. It just has to be an isometry. As long as the columns of the matrix and the rows are orthogonal, it doesn't have to be a square matrix. I could have more of the n's than the m's, and that's fine too. We'll see an example of that at some point. And if the map is trace preserving, then what we have is this condition, the sum of m dagger m's is the identity. Okay? And that's a trace preserving map. Not all CP maps are trace preserving, but typically those are the ones we're typically most interested in. How could the trace not be preserved? Well, if we're only looking at a subspace of the whole Hilbert space, it might be the case that through the interaction, population goes to another subspace. An example of that is, I'll just draw over here, if I have, let's say I have an atom with some manifold of multiple ground states where I can absorb light and I can spontaneously submit to two different spaces, but I'm only considering this subspace as the space of interest. Then through the open quantum system, I could pump into the other, it's called optical pumping or spontaneous scattering, and then I'd lose population from this subspace and it'd end up in here, and that map is not trace preserving. So it depends. I can have a perfectly physical map that's not trace preserving if I choose to only focus on a subspace of the whole Hilbert space of the system. Okay? Right. Okay, so Krauss maps arise from a measurement model, and the Krauss operators are given here. So the Krauss operators are partial matrix elements. They are matrix elements of my entangling unitary that couples the system and the environment between the fiducial state and some member of a basis for the environment. Okay, so I've chosen a set of states which is a basis for the environment. And that's maybe one thing clear. I could choose any basis I like, and different bases will give rise to different Krauss operators, and it might even be an over-complete basis, which is another reason why they don't have to be, doesn't necessarily have to be the same dimension. But for some given basis, there's some set of Krauss operators, and that defines the map. Okay. And another way of writing the open quantum system is what's called the unitary representation, which is to say I start with I look at the action of the entangling unitary on a product state, where I have an arbitrary state of the system and I'm in the fiducial state of the environment. I ask, how does this joint thing evolve? It evolves into this. So for every basis state in the environment, the Krauss operator acts on the system. Is a correlation between this state of the environment and this action of the interaction on the state. Importantly, what we see is that through this, why I call it this will generally be an entangling interaction. The system and the environment. If I start the system in a pure state and the environment in the pure state, then they become entangled, because they become correlated. And anything that's correlated is entangled if you start it in a pure state. Okay? And that's important because, as we described, when you have an overall bipartite system which is correlated, therefore entangled, if you look at a subsystem, it will be mixed. So the state of the system, this is the map on the state of the system, is a mixed state, generally. And it's a statistical mixture of these states. Oops, this is not what I meant to write. That's what I meant to write, excuse me. It's a statistical mixture of these states. Each of these states is the action of each of the Krauss operators. Because the Krauss operator is not unitary, I must renormalize the state after the action to find out what the state is. And the probability in the statistical mixture is given by the norm squared of the Krauss operator acting on that state, which is equivalent to the expected value of n diagram. Okay. So this is some useful mathematics. We're going to develop more physical intuition about this, I hope, today. But mathematically, what we have, all these things are equivalent. I could say it's a CP map. If it's a CP map, it's a Krauss map. If it's a Krauss map, there exists a measurement model that describes it. All those things are true. It's somebody or other's theorem, I don't know. All right, maybe Krauss. All right, or Gottesman, I don't know. All right.
Turns out it was Carl Friedrich Gauss 3
Yeah, right. Okay, let's talk about this business of a so-called measurement model. And for that, we go back to the founder, our God, von Neumann. So von Neumann had, a quantum description of measurement. So, what we're typically taught when we learn about quantum measurement is we think about observables. And those are permission operators, which have, for example, some set of eigenvectors and eigenvalues. which are positive, not positive, real numbers. Okay. And we want to do a measurement that measures this observable, right? And what we're typically taught is, okay, if I measure an observable, if I start in a state which is generally some superposition of the eigenvectors, and I want to know what, if I measure I will find the eigenvalue A with the probability given by the probability amplitude squared, or equivalently, this is the Born rule, where this is the projector onto the eigenvector. Okay. Right, that's what we all learn. And moreover, we learn after we find this eigenvalue, the system collapses, right? There's a collapse of the wave function. And if we find this eigenvalue, which happens with that probability, the system collapses onto the specific eigenvector associated with that eigenvalue, right? You guys still learn that? Yeah, it's kind of, yeah.
Well, if you're looking at Valentin's text, right?
Okay.
I'm sorry.
Yeah. What is why? You must have asked me, why did you choose Leslie Valentine?
Well, I mean, at March reading, the publishers section, they had that like front and center.
Oh, jeez. Okay. All right. Let us continue. Right. So now, you know, I mean, I wasn't there at the time, but you know, but basically, as I understand it, you know, what von Neumann was trying to do is say, well, okay, this is not some magical thing. We can try to understand this from the point of view of quantum mechanics, where there's, you know, we have a system. The system is described by this state, for example, and we do a measurement. There's a meter. But the meter, we should think about as a quantum mechanical object as well. And, you know, so this is my A meter. It's going to measure the observable A. And so what it should do is, you know, I start out the system in some state initially, and then it gets coupled to it, and the meter will move to, the needle will move to some other state that depends on A. And then I'll look at the meter, and if it moves over here, and I have, you know, little ticks on this thing that tell me which value of A it's on. And if I see it's there, I say, okay, it measured the value A. And after I do that, the system, I say for sure, the system is in A, according to that. And I should get that with this probability. So you can try, so the von Neumann measurement model is very straightforward. What this kind of measurement is what's called a quantum non-demolition measurement, or in modern parlance, in the sense that if the system was in an eigenvector of A, it shouldn't disturb it. It shouldn't demolish the state. There's the term QND is kind of a leftover from something completely different, back action evading, whatever the hell that meant at the time. But it still sticks. People talk about QND measurements now. So what we want is something that if the system is an eigenvector, shouldn't change it, okay? So what we're gonna do is the kind of thing we described over there, where I have my this is gonna play the role of the environment, okay? That is to say, there's a coupled system to something else, the ancillary system, which in this case is the meter, and I'm gonna have some entangling system-meter interaction. All right, and what would I choose this to be? Well, what I wanted to do is I wanted to say displace the position of the meter by an amount proportional to the eigenvalue A, okay? So if I think about what the physics of that is, if I just think about the meter as being displaced in position, what is the generator of displacement in position? Momentum, thank you. So I'm just gonna write this thing as e to the minus a tensor p of the meter. Now, maybe there's some coupling constant. Maybe, you know, it depends how strong that coupling constant is. So what this unitary does is it displaces the position of the meter by an amount proportional to how big A is. And that, if I do that, I should get something that does the right thing, okay? So what I want to say is this is very much equivalent to that unitary representation of my channel, where I say there's some state of the system and the meter is in some fiducial state, which is I've initialized the meter, you know, where if there's no interaction, it's sitting there. I've calibrated things, you know, there's some dials here. You have to dial it up and, you know, get the meter to be right at 0. Keep doing it, all right? So there it is. And let's just see now, if my system is in a superposition of the eigenstates of A, then that's, I just plug that in, okay? I just said there's some superposition. And now I'm gonna make the action of this, I'm gonna bring it inside, this inside here, and I have e to the minus I chi A tensor the momentum on the meter acting on A tensor the fiducial state of the meter. Okay? Now, this vector is an eigenvector of the operator capital A with eigenvalue little a. So I can just replace that with the eigenvalue A and then move it through to the next action. I replaced this by its eigenvalues, right?
P is the momentum vector.
P is the momentum operator
Yeah.
that acts on the meter, the needle, right? It's displacing the position of the needle. So what I get here is a state that I'm just going to call phi sub A. That's this guy. Right? It's the state of the meter that's been displaced by an amount proportional to A. I mean, it's not exact, I mean, how much it's displaced depends on, I'd have to recalibrate, right? You know, whatever I mean by these ticks on the meter would have to be calibrated depending on the strength of the coupling, how far it moves, but So it's labeled by A, the eigenvalue little a, okay? So what we have found in this is that the joint system of the system and the meter after this interaction is an entangled state. It's a correlated state, but it's also an entangled state, where the meter is moved to someplace centered around the value A that's been calibrated, depending on whether the system was in that state A. For every possible outcome little a, the meter could move to a different position. This is entangled. Okay. Now, I can then ask, okay, now I look at the meter and I see where it is. Because ultimately, nothing has happened. I mean, the von Neumann measurement model, as described here, doesn't solve anything because nothing was measured, so to speak. It's just been correlated. The system and the meter have been correlated. Has the measurement occurred or not? That's maybe another story we can talk about and we'll get into. I mean, this is sort of where the whole theory of decoherence came from. Was the notion of the pointer states, if you've ever heard of them, came from thinking about exactly this thing, the pointer of the meter. But literally what happens is, here's my eyeball, I look and I see where it is. So I've done a measurement now of the position of the meter. So I'm gonna look in the position basis and say, where is the meter? And when I find it in one of these places, the degree to which the meter is very well defined and there's no two values of A that the wave packets would overlap, then when I find the meter in this outcome, then in the same way that the EPR correlation, the system would collapse into its correlated state. Ta-da! Collapse of the wave function. Okay? Moreover, the probability that I'm going to find the meter here is just the square of this amplitude. So this was von Neumann's saying, there's nothing special, this is how it works, this is how it works. Now, it doesn't really solve anything, really, in the sense that this step was magic, right? We did a measurement, and the fact that it collapsed into that is the magic. We just moved it up there, but at least, what's important about this is that there is a physical interaction between two things that actually is the measurement. And this is important because, for a reason I'll explain right now, and its relationship to the open quantum system channel. So, all quantum measurements are done, I would say, indirectly. We have some quantum system we want to know something about. The way we do it is that we probe it in some way. There's something, maybe we're shooting neutrons at it. Maybe we're shooting photons at it. We're probing it in some way, and then ultimately we measure the probe. And the probe we measure in some basis. When we look at the meter. So I mean, even the quintessential example that we all learn when we say do the Stern-Gerlach, it's typically shown as like the prototypical example of what a quantum measurement is, right? In Stern-Gerlach, you say, oh, I have this, gradient magnetic field, and I, send in these spins here, and they either go spin up or spin down. But what do you actually measure? Well, you measure where it is. What you're actually measuring is the position of the beam. And the position of the beam is correlated to the spin, but it's really what you're measuring is the position, right? So every measurement is like this. So that's important because we also want to describe the right way to calculate the probability of measurement outcomes and how we should update our knowledge conditioned on that measurement when we do a real measurement in the lab. You don't understand what a quantum measurement is until you've actually done a measurement. So I've worked with people who do measurements, and it's just been so informative because I just understand much more what a quantum measurement is because I know how measurements are done. So let's just think about this a little bit more now. What's nice is that when we connect this to our formalism. So when we do this kind of indirect measurement, I have my system and my meter. I prepare the system somehow. The meter is in some fiducial state. And then I do a measurement on the meter in some basis, like the position basis, for example. And I say, okay, what we just said is we have the unitary representation of this. I can then ask, what's the probability of seeing mu on the meter? Well, the probability of seeing mu on the meter is will be equal to the norm squared of this. That's just the rule, quantum mechanics. But that's nothing more than this, which is what we said a moment ago. Was that. So when I do a measurement of the quantum system indirectly by first entangling it with a probe and then measuring the probe, the probability of seeing that is not the projector on some eigenvector of the observable A in general. It might limit to that. You'll see that in your homework. No one loves that more than Brandon. But in general, this is not equal to a projector. As we were taught that a measurement is a projection. The measurement outcomes here are determined by these operators, which I'll call E mu. Those E mu are m dagger m. And the probability of seeing mu is the trace of rho of the system with E mu, where rho of the system in this case is a pure state. It doesn't have to be. I could have started this. And the sum of the E mu's is the identity. So what we have shown in this indirect measurement is a way of understanding how, when I learn something about the system, the probabilities of those outcomes are not necessarily described by Hermitian observable, but by some resolution of the identity in terms of positive operators, is what we call the positive operator value measure, or a POVM. A POVM can always be realized through an indirect measurement model. The E-mu's are called the POVM elements. They're the elements of the POVM. The collection of such operators makes it the POVM. And we can understand that POVM as I've entangled the system with the probe, and then I do a projective measurement on the probe. The outcomes are, all I care about is two things. One, what possible outcomes could I get with what probability? Okay, so I've said there's a POVM labeled by outcomes mu, and to calculate the probability, I do this. This is the Born rule. It's the generalization of psi star psi. It says I get this probability by looking at the trace overlap between the POVM element and the state of the system. There's a second thing I want to know. Okay, I found mu. I might want to do another measurement later, throw another probe at it. And to do that, I need to know what's the state of the system conditioned on the fact that I found mu. Which we might call psi sub mu. Well, that's the partial matrix element of this renormalized, because and if we look at what that is, that's equal to, according to this, if we look at this, it's mu acting on the system. Renormalized. This is what I like to call quantum Bayes' rule. We'll see this also maybe more in homework. What is Bayes' rule? Bayes' rule says I have a prior probability distribution. I learned something. What's my posterior probability distribution conditioned on the outcome I saw? That's what this is. And it says if I do this indirect measurement on the system, then conditioned on that outcome, I apply the corresponding Krauss operator to the system and then renormalize. It's equivalent to as you'll see, this is like the conditional probability, this is the prior probability distribution, and this is the renormalization. This is the quantum version. If everything commutes, this is exactly Bayes' rule. It's when they don't commute that it's interesting. That's when there's something different than we have. That's when back action is different. That's a whole other story of interesting. To what degree is back action just a figment of your imagination, and to what degree is it physical? Well, maybe we'll talk about that over some beverage. Right. So this is why I like to call the Krauss operators the measurement operators, because they are the operators corresponding to what happens when you do this kind of interaction. If I know the Krauss operators, I know everything, because the Krauss operators both tell me how to update the state conditioned on the outcome. They also tell me what the POVM is, because M dagger M are the POVM elements. If I just know the POVM, then I don't know how to update the state, because I can't know what m dagger m is. I could write the POVM, the m as the square root of E, but that would not be the complete story. I need to know the measurement model if I'm going to know how to update the state properly. Okay, the last thing I want to say in relation to the measurement model is, what does this have to do with an open quantum system? So what we just said is there's this indirect measurement. The probe has a record of the system, and then we look at the probe. We can think about an open quantum system or a quantum channel as the environment measures the system, but we don't know the result. Now we can ask, if we don't know the result, did the measurement really happen? But that's another story. Operationally, what does that mean? What it means is, I have the quantum system. I have the environment. This is like the meter, the big old thing with the dial on it that we were looking at over there, which has a record, but we don't know what it is. If we looked for it in the environment, we might find some particular value mu of the environment. But since we don't know, so let's say the environment says mu. That's correlated to something about the system in what we were just describing over here. But we don't know which one it is. If it says mu, then we would say for sure the state of the system is in the sky. But we don't know what that is. So if we don't have the information that potentially exists there, but we didn't seek it out, then we can't assign this state to the system because we don't know what value mu is. But what we do know is that the system environment interacted, and for every value of mu that the environment could have been in, there is a corresponding psi mu of the system. And so the state of the system, since we don't know that, since we don't know mu, the state of our system should just be a weighted average of the possible mu's weighted by the probability that that mu happened. We should just look at the statistical mixture of the possible ones. And that's equivalent to tracing out the environment. This picture is going to be more important. It's both useful conceptually, but also we'll see calculationally and numerically. And the whole story of quantum trajectories is this story. That is, the environment has done a measurement on the system. We don't know what that measurement outcome is, so we have to average it appropriately. If we looked at the environment and found that, then we would have a back action that is described through the quantum Bayes rule. And that would happen with the probability given by the Born rule.
And we can also have an intermediate case where maybe we get some.
That's right, and that's important. It's very important that, you know, we're saying, these Krauss operators don't necessarily fully collapse the wave function. They might only partially collapse the wave function. We can kind of see that going back over here. Suppose that I had a big fat chubby wave packet that wasn't really well localized around some position. And there was a weak coupling chi such that it only moves slightly, and there's a big overlap between those two wave packets. Then when I see the position of the meter, I'm not sure whether it was here or here because there's enough overlap between those wave packets. That's an example of a non-projective measurement, and it could be a very weak measurement. If this wave packet is very broad, then I will do very little by learning the position. I might tweak it a little bit. Those are called weak measurements, not to be confused with weak values, which is another story. Excellent. So this is a nice picture that this is why we like to call the unitary representation of the channel a measurement model, because I can think about it in this measurement language. This language in which the environment has a measurement record available for us to look at, but we don't look at it. And when we don't, if we did look at it, we would get certain back action. If we don't look at it, then we get this mix, this kind of mix. Okay. All right, very good. Oh yeah, that's what I was going to talk about. So let's talk about important examples of quantum channels. So let's talk about quantum channels on a qubit. Okay, so my system is a two-level system. So there are channels that we often use in talking about, you know, just mathematical models of quantum channels. And we'll talk more next week of how some of these channels arise physically. But some examples we talk about are a depolarizing channel. One way to describe a channel is just to say, what are the Krauss operators? Or what are some, of course we can have a different set of properties, not unique, but if I give you some set of Krauss operators, that defines the channel, okay? So the Krauss operators that define a depolarizing channel. Remember, any operator acting on a two-level system can be decomposed into the identity and the Pauli's. So my Krauss operators act on my two-level system, so they're going to be the identity, or I can always write them that way. So this is going to be my set of Krauss operators. Where P is a number between 0 and 1. So let's write out, these are my MUs. These are my Krauss operators. And so for a depolarizing channel,
Wouldn't the identity be 1 minus p, root 1 minus p?
sorry, thank you, Ivy, absolutely. Yep, indeed. And that's that, so what we have then, the sum over mu, mu, rho, mu dagger, and this is equal to 1 minus p times rho plus this p over 3 sigma x plus sigma y plus sigma z. So this is what's called a depolarizing channel, which I can think about with probability p, nothing happens. And with the remaining probability, either I get, the state gets hit by sigma x, or the state gets hit by sigma y, or the state gets hit by sigma z, and it happens equally. Now, when thinking about quantum channels on a qubit, it's nice to think about what happens to the Bloch sphere. This is another problem you'll have for homework. So if I start with a qubit, okay, a qubit, the arbitrary state of the qubit can be written in terms of the Bloch vector. If I start on the Bloch sphere as a pure state with unit length, then the action of the channel is, no matter where I start on the Bloch sphere, I get more mixed equally. The length of this vector just shrinks. That's why it's called depolarizing. And when p equals 1, then I go to the identity. Okay? So the state of the system goes, maybe I'll just write it like this. And it shrinks. So the Bloch sphere just shrinks towards the origin. That's a depolarizing channel. All right. Okay. Another example is a dephasing channel. What would we think that means, just physically? What would it mean to say something is dephasing?
Takes away the phase.
Takes away the phase. What phase are we talking about? That's a good.
Relative polarization.
Yeah, something about the relative phase, right? I mean, if we have, a state which is, say some superposition of spin up and spin down, say as a pure state, and I looked at what the density matrix is, I have the diagonal elements, but then I have the off-diagonal elements. Where this is equal to something that depends on the relative phase between the amplitudes of up and down. So we remember that on the block sphere, the representation has to do with how big the relative phase is, has to do with the x and y components of the block vector. The z component of the block vector tells me the relative population. The x and y components tell me about the relative phase. So we would expect for a depolarizing channel to be something that would shrink the block sphere into a kind of ellipse that looks like this. And the more depolarizing it is, the more I lose the relative phase, and I only know what the relative population is. So a dephasing channel should kill off the off-diagonal elements of the density matrix. That's getting rid of the phase, that's taking away the phase. So the Krauss operators that do that, a dephasing channel, has something where it would leave the z component alone, but change the x and y. So the only Krauss operator that does that in a Pauli matrix is sigma z. So a dephasing channel has as the Krauss operators, it has an M0, which is the identity, and an M1, which is sigma z. And it takes anything on the block sphere and takes away the phase, okay, and leaves only the relative populations. That's a dephasing channel.
They call it a block, but it's the same as a Poincare sphere.
It is, yeah, it's the same thing as the Poincare sphere. The block sphere is for spins, the Poincare sphere is for polarization, but they're isomorphic mathematical structures. Yeah, it's exactly the same thing. Very good. There's one other channel that we care a lot about, and that's the amplitude damping channel. The amplitude damping channel, what would it do? Well, it's like spontaneous emission. That's an example of an amplitude damping channel. So if I think about the excited state as equivalent to the spin up of the qubit and the ground state as equivalent to the spin down of the qubit, and I start here, then through spontaneous emission, I damp the amplitude in the excited state. The probability in the excited state as a function of time, we know, decays, and it damps. That's why it's called an amplitude damping channel. What are the Krauss operators that would do that?
Some probability that you have to, another probability to do a projection.
We flip, right? So, I mean, clearly this has to do with something like a sigma minus that takes the spin up and spin to spin down, right? We want something that does that with some probability. So I can think about one of my Krauss operators as, with some probability, I flip the spin. And then I'm just going to call M0 1 minus that. 1 minus, so what I have is that I need to have M I'm gonna think about my Krauss operators in this way, because I have to have the sum of them if it's trace preserving, right? And this is the projection onto the excited state. So this is one way I like to think about a amplitude damping channel, okay? So that tells me that this guy, for the amplitude damping, with some probability, I flip the spin from down to up. And then I have which is equal to, let's see, I can write all of these different terms out if you like, okay? Question for you, what if P equals 1? If P equals 1, and I want to know what is the action of this channel on this, then what do you expect? What's the state of the system if the probability of this jump is 1, for sure? What would the state of the system be after that?
You're just gonna end up spin down.
It's be spin down. So, an important aspect of this is that the amplitude damping channel can also purify a state. If I started in a mixed state and I have amplitude damping, at the end I have a pure state. That is to say, I can cool, right? An open quantum system can change the entropy, but it doesn't have to heat. It could also cool. And this is sort of an effect. Laser cooling is such an example, where you can scatter photons and take entropy away from a system and cool it through the process of amplitude damping. In an amplitude damping channel, what happens to the block the box here is it kind of becomes a little eggplant down here. So this sphere, I should make it blue so that it's consistent with all the other ones. This thing gets shrunk in this direction. Okay? And then ultimately, this center will end up right here at the very end. So one of the things that will be important in our discussions is, okay, we wrote down these channels, but how do they occur physically? Let's, I just want to, I think we're going to end a little bit early today because I don't want to start the next topic in the next 10 minutes, but I just want to maybe explore for a moment. What kind of physics would you imagine would cause dephasing? I mean, we said spontaneous emission is an example of an amplitude damping channel. What about dephasing? Where the heck would that come from? Anyone have some thoughts about that? Yeah. Yeah, so, I mean, firstly, what's happening here is something that is affecting the relative phase between spin up and spin down, or whatever the two qubit states are, without affecting the population. So something, how would you get something that caused that? Well, I mean, as Robbie was suggesting, if I thought about a real spin, let's say I have a spin in a magnetic field. This is the Hamiltonian. Right? And depending on the G factor, whatever spin, whether up or down is a line, let's say I have a negative G factor, so spin up goes up and spin down goes down. And there's an energy difference here. Right? So, you know, I might say the state of the system as a function of time okay. And there's a relative phase here that depends on the relative energy. But suppose the strength of this magnetic field fluctuated a little bit in some random way. Then what I'm going to do is I'm going to get a delta E here and a delta E here that depend on the little variation in the magnetic field. Maybe there's 60 hertz noise around it and it's shielded properly. And it's going to fluctuate this, it's not going to change the population in either one. I should really say maybe there's some amplitude here. But it's going to change the relative phase. And if I don't know what that relative phase is, then under some appropriate averaging, that would be a dephasing channel. You remember, maybe, from last semester, we called that a T2 process, right? So the T2 time that one thinks about in a qubit or a two-level system is related to the phase coherence between the two states. And if there's anything that shifts the energy or causes a phase accumulation of the amplitude that we don't know, that we haven't kept track of properly, that we haven't zeroed out in some way, will cause that, and that's a dephasing channel. What about a depolarizing channel? Does anyone have an example of a physical process that would cause a depolarizing? Yeah.
Shining polarized light on a rough surface depolarizes.
Well, actually, that would be more,
That's more optical.
but it would be more dephasing than depolarizing. It would change the relative phase.
But if it's random, then it's depolarized.
Well, the term it's true, but I've lost the polarization. But in this formal sense, it's not exactly the same thing.
I'm guessing heating.
So there's another way of writing the polarized
Yeah.
channel, where you can, for the qubits, you can say with some probability it's rho, and then with some other probability we just replace it with the identity matrix with
It's completely mixed state.
Kind of seems like heating, right?
If I heat something, so I mean the thing about the polarizing channel is I should take as Cole was saying that it's maybe Victor, maybe your rough surface, maybe that is equivalent. I need to take it ultimately to the completely mixed state, right? It needs to become completely mixed. The dephasing channel doesn't necessarily take it to if I start in a state that is, yeah, so I think actually, Victor, you're correct about this. What's different about a depolarizing channel versus a dephasing channel?
The random fields are in all directions in some sense for the depolarizing channel.
End up with a completely mixed depolarizing channel.
In a depolarizing channel, there's what I think one thing that's important is that if I started in a state that was at one of these poles, it doesn't change. So if I started, all spin up or all spin down, which would correspond in the polarization case to say fully horizontal or fully vertical, it doesn't do anything. It only does things to, anything that is a superposition of those two. So I think, Victor, you're absolutely right. In the case of something that would make it a completely unpolarized state would be a depolarizing channel in the optics example. That's a good example. In the qubit case,
So this dephasing here, this is only in the example for dephasing, this is varying the magnetic field,
yeah,
but it's like the direction of the magnetic field is the same.
I'd have to somehow be also I think so. Alex's example about heating, if I put this in contact with a thermal bath that was at infinite temperature, then it would end up with an equal up and down mixture. One of the points I wanted to emphasize here is that we rarely have a depolarizing channel. That's just not a physical channel that typically is what's going on.
But it's easy.
But it's easy to talk about because we don't, as Cole was saying, there's many ways to write a depolarizing channel. Here, in some sense, because I just made this equal x, y, and z, I haven't made any specific, and I can think about what's important for a depolarizing channel is that if I start with a pure state, I can think about through a depolarizing channel, with some probability, I do nothing. And with some probability, I put it in the completely mixed state. For 1 minus that. Okay. Depending on, so, actually, I think I want it the other way around. So what this says is, when P is 1, I've just completely depolarized it. It's completely mixed state. So I can think about the depolarizing channel as something which just puts white noise on top of the state. That's a nice mathematical thing. Are there physical processes that do that? It's really kind of crazy. Suppose that this state was not the state of 1 qubit, but the state of n qubits. And it was a highly entangled state, like something that came out of a random circuit. Then what it's saying is the depolarizing channel doesn't change in any way which bit strings are the most likely and which are the least likely. It only adds a constant background. It's like saying I have a speckle pattern with, crazy probability. And then when I put this through the channel, all that happens is there's a constant background on top of it, but I didn't change where any of the peaks were. That's how Google's quantum supremacy works, because they assume this is true. Is it a good assumption?
Doesn't seem like it.
Yeah.
So physically, is the depolarizing channel equivalent to applying random magnetic fields in random directions?
Yes. Correct. Yeah. Yeah.
What I was thinking when I was mentioning heating is like if you have a ferromagnet and you're looking at the state of, say, one individual spin, as you start out, if it's magnetized, it's going to have a well-defined direction. And then if you heat it up past its Curie temperature, now the state of your spin is gonna be like a totally mixed state, right? It's gonna be random. Is that a good example?
No, I don't think it'll be it won't be completely mixed. It will be a given state, which, you know, will have some, it won't be a completely mixed state with completely random directions. It will depend on, I mean, it sort of depends, you know, if I have to think about what the Hamiltonian is, whether at a certain finite temperature, the state has any polarization at all.
I guess I'm thinking that this might not be correct, but like above the Curie temperature, the spins are just totally random.
I think it, yeah, I mean, it will really be, I think, I have to think about that. I mean, you know, this of course will depend on the Hamiltonian, whether, you know, if there are straight magnetic fields of any kind, they will have some polarization. To say that something is completely mixed is to say it has infinite, it's at infinite temperature. So I don't think that's true, that it'll be completely random in that case. But it is true that, you know, when you have something in contact with some thermal reservoir, it will tend to, you know, both be an amplitude damping and an amplitude increasing channel at some detailed balance to the degree to which it becomes completely mixed. Anyway, we're going to talk a little bit more about, I mean, so where are we headed? We're headed now, we want to think about where these channels come from a physical point of view. And importantly, what we're interested in is the dynamics, right? So right now we just said there's an input and output, but we haven't really talked about dynamics from the point of view of the time evolution of the system. And so we're going to revisit our friend, the optical block equations and other such equations from first principles and see how we derive them from the point of view of these CPMs. All right? I'll think about your question a little bit harder.